So here we go. Our first device is a diode, which is essentially a PN junction, and all of you are aware that all these days for a month or so we have been doing a lot of semiconductor physics. The idea was to understand what goes in PN junction. Those theories are required. So once we understand how carriers move, now you have two kinds of semiconductor types, P and N, brought together. First time that's what we are going to do, and we actually observe that it represents our electrical device, which is called diode. And if we see the IV characteristics, let's say this is grounded and this can be plus minus V. So if I apply a voltage across a diode, plus or minus as shown, I figure out when this was plus voltage, I see a characteristics of the diode as initially very small current with certain voltage, and this voltage is what we will call as cut-in voltage, V gamma, okay, up to which we say the current is very small, or what we will call later the leakage current or saturation currents. Then beyond this part of it, actually first there is another part up to this where this follows a law which is e to the power qv by 2 kt kind of relations. Then when I go beyond this region is e to the power qv by kt. Further, this part is again e to the power qv by 2 kt, and then saturate. So essentially, I see four regions in which diode characteristics operate. Okay. Below V gamma, the current is extremely small. This saturation word is not with IS, it is I is getting saturated. Whereas this current essentially will be related to what we call I sat, the saturation current of the diode. Okay, we'll see why the name was given. And beyond this, initially you get e to the power qv by 2 kt. And e to the power q, proportional, all is proportional, okay. Not there. So we say initially e to the power qv by 2 kt, then ev by q kt only, qv by kt, and then again to qv by 2 kt. So obviously there are different phenomena that are going on, and we like to know what are these phenomena which makes IV something like this. This was slightly shown wider and something, it's not that wide, it's actually comparatively very sharp characteristic is seen, and we observe that in ideal case I would expect at V is equal to 0 almost infinite current to flow. This is an ideal situation in which anything greater than 0 the current should shoot to infinite. If I seek equivalently on the reverse bias, which I call when the potential is negative on the, it was first positive, now it is negative, because this is called cathode, this is anode, equivalent of the old diode names. Earlier there used to be vacuum diode and we used to call anodes and cathodes. Cathode means emitting electrons. So same name we continued. So if we say this is our cathode, then if I bias cathode positive and anode negative, then I find that for a while, for a large voltage V negative, the current is very small, same as what saturation currents are. So to some extent these two currents are similar, these currents are similar, but you will be surprised to see later in theory that though I obtained the same expression, same current values, the expression wise they are different, but they give the same current. I won't say same, they have same values, but it turns out to be the physics for this is different from physics for this, but the value you get is same. Okay, that's the trick of the game. Okay. So if I see larger reverse bias, I find that the current is very small, and therefore it continues for a while, maybe compared to this voltage maybe around 0.75 maximum, whereas this may be around 30 volt, 50 volt, 100 volt, 1000 volts. Okay. A power diode rectifier, as it is called, can stand up to 5000 volts. Okay, so it's not that it's only 1000 or something. Any number could be very large, depends on the design. And at this value, what we call breakdown, suddenly current starts shooting. So it's called breakdown. So device in reverse bias otherwise was having very low currents, but suddenly starts shooting the currents, and it's called breakdown. So if I assume something here very small, ideally I am looking something, it's going like this, and its ideal diode characteristics, ideal, never occurs. The real characteristics is shown there. Ideally it looks something like this. So essentially till this value is reached, this is equivalently saying it is like a switch, on, off. Okay. So a diode acts like a switch. Okay. In ideal state, slightly positive, infinite current, short circuits. Slightly negative and any amount rather for larger value, no currents. So ideally diode looks like a switch. Why we are interested to look this switch? Because if we are looking for digital circuits, what exactly we are creating? 1 or zeros as the two bits, on and off. Okay. So I can now see diode can act like an element for switching as 1 zeros. Okay. However, the only problem why diodes were not used as much as this element for digital circuit was there is no control. Only control is the change in polarity. If I want at a given way it should turn on and turn off at a given time, then I need the third terminal, and that's how we went for transistors, the third terminal. But basically diode can act like a switching element. Now, why we are looking into it? Because if I want to explain why this is occurring, the slopes are changing, or why this is blocked for a while and then turns down, I must then revert back to my theory of PN junction and try to see how do I get these characteristics. Is that point clear? So what is the importance is that at the end, so ideally, even if it is not ideal, we can still say this is some kind of equivalent, still we can write. You can say pseudo-ideal, close to ideal but not really ideal, and we can also give some slope here. Okay, we can also give some slope here because the current essentially, though it looks as if it is constant, it's not. It is increasing in negative direction but very slowly, very slowly. So if we see equivalently this, you can say in the forward bias the diode looks, if this is the slope of this characteristics, then this is a RF plus a cut-in voltage as equivalent of a diode under forward bias. A diode can be represented as a small battery of V gamma, because unless V gamma reaches, the RF doesn't start, or RF is infinite, and zero in fact, infinite, and when V gamma crosses, then the current starts moving. So this is the equivalent of a diode under forward bias. Equivalently, unless you reach VBR, for all practical purposes, you have RR as the slope of this characteristics. How much will be value of RR? Mega ohms, because it's a very low slope, so it's the order of mega ohms. Okay. Whereas typically this RF may be order of tens of ohm to hundreds of ohms. Depends on the fabrication I do. I may get tens of ohm, or in some cases even 1 ohm, okay, or even less than a ohm. Different tricks to make that. So essentially what I was expecting this to act like a switch, RF 0 and RR infinite. When I open, RR infinite, when I short, RF is 0. This is what an ideal switch is. So in all of a design of a diode or design of a PN junction, what are we trying to achieve? Low RF and high RR, because then I am getting an electrical equivalent which I am looking for a switch. Is that correct? So design of a diode essentially looks for smaller RF and large RR. Large breakdown, because if I have a 3000 volts to block, that V breakdown should be larger than 3000, because then only it will block for that voltage. Is that point clear? So this is what circuit people are asking from us. So now we'll say, okay, how close we can come to you so that you can represent the diode in a circuit form. If you can, once you know this, so any diode circuit, all that, for example, a simplest circuit could be, let's say, I apply a signal, like this is my output voltage V0, this is my R load. So when the positive cycle will appear, what will be the status of a diode? When the positive cycle appears across the diode, this is forward biased. Is that clear? It is forward biased. When in forward bias, right now we assume V gamma is very small compared to the peak value of this for the simplicity. We can always subtract that value. This is, remember, it will always get subtracted. Why? Plus minus, so it will get subtracted. Assuming that V gamma is close to 0 for a while, so we may say the equivalent will be RF or V sin omega t or cos omega t. Only thing is we are only looking for positive cycle. Call it VAC, signal applied. This, how much is the R output here? V0 is R upon RF plus R times VAC, positive cycle. Actually for even negative the formula will remain, RF will be replaced by RR, and that's that. So essentially if I look at the output voltage across VR, V0, I find, of course this, if RF is very very small, how much will be this V0? Same as VAC. But if RF is finite, this value will be slightly lower, but assuming whatever it is, this will follow the signal. The peak values will be, the values will be proportional to R by RF ratio, but otherwise it will follow same things. However, if I apply negative potential now, VAC is negative cycle as we go up ahead. We figure out now that in reverse bias, the diode polarity is something like this. In the negative cycle, the diode now gets reverse biased. Ideally, if RR, like I assume RR infinite, okay, so it opens, but let's say even if RR exists, this resistance will become RR in the reverse bias. Now, since RR is much larger compared to R0, R, assuming RRs have hundreds of mega ohms or at least tens of mega ohm and R is kilo ohms, this is close to 0. If RR is much larger than R, this value will be closing to 0. Essentially it means in this cycle output voltage is not available. Slightly available, but practically no available. So you now say you have an AC signal. At the output, you don't have AC now. What is difference between AC and DC? AC means it's alternating between plus and minus. Okay. DC means unidirectional. It does not mean constant. It's a unidirectional current. So this voltage is now unidirectional. So you have now converted AC signal into a DC signal, and if I put some capacitance, I can even make a DC value fixed to if it charges to maximum value, it will become constant DC value as well if I need. Okay. Or I can take an average of this and find what is the average DC from this cycle. Is that point clear? So essentially a diode acts like, this operation is called rectification. This operation is called rectification, and diode is therefore called rectifier. Conversion of AC into DC is called rectification, and the diode therefore is called AC diode, rectifier. And larger the breakdown voltage or larger the voltage it can sustain, it will be then called power rectifier. That's what all lines in the everywhere, you use megavolts, it may actually stands. Some of them, not all, not one, multiple of them, banks of them. Is that point clear? So this is what essentially circuit we are looking for. This is what is going to happen with the diode. Either it can replace this as a switch, so I am looking as a logical element, or I am looking into this. Then I can also look at it, if I put some more components, I can play with the shapes of this. Okay, I can play what we'll say later, the words clipper, clampers, limiters. We can actually tailor the outputs. Okay, we may do something like this, that it looks something like this, which is like a pulse. Okay, so I have methods later in the circuit, by using the same diode plus some RC components, I can convert it into a wave of my choice. Okay, this is essentially what diode allows you to do, and therefore diode is very, very, very important element in all our circuit analysis. Is that clear? Because firstly, as a simple rectifier, it allows AC to be converted to DC. Just put a diode half the cycle, it will allow, half the cycle it will not allow. It will not allow has to be understood. In reality, I keep saying, there will be something like this, because RR is finite. Okay. But if RR is much, much larger, tending to infinite compared to R, then you say it is almost no voltage at the output. Or to say switch opens, so the output remains C. Okay. This is what we want to do circuit wise, and to do this, what value of RF RR I can get, how do they control the voltage, is that what we are interested in. So we now go back to our devices and see how this circuit could be, circuit element can be realized, and therefore the next part is to understand how PN junctions behave. Okay. We said PN junction act like a diode, so fine, let's see how PN junction really act like a diode. This is circuit requirements. So as an electrical circuit person, I am least bothered how do you get this. As long as you give me this equivalent circuit, for me things are over. Okay. I just, wherever you put this element, I will replace it. Then I will solve a network. I am solving a simple network. So I can always solve a network once I know equivalent circuit. Is that point clear? These two are called equivalent circuit of a diode. Is that clear? So we all the devices we do, at the end we must find out its equivalent circuit, because then only I can replace in a circuit that element, and if I replace it, then I can solve network easily. That's what I know, understand, I know Kirchhoff law well, and therefore I can always solve any network very easily. Okay, so this is a preface to what PN junctions we are looking for, to show you where we want to go at the end. Okay, and to go there, we like to see how PN junctions behave, or why they behave the way you want or you don't want. Sometimes you don't want, it will behave that way. Sometimes you want, it may behave that way. So it depends on how good you can make device. Okay, so is that issue clear, that why we are looking into equivalence, why we are trying to see the theory? Because I want to create these values of my choice. Electrical engineers do not like someone giving them something they don't want. So we want to know, can I get what I want? So here is what we will do now. The first thing we'll like to do, maybe I have made a small list. The way I will now go, I first give you something, introduction, आज दिया भी. Then I will actually give you how diodes are made. Then I learn basic physics of p-n junction formation. Then I look for transport, and finally I may look for some applications. Introduction I did. Now we start with fabrication. As such, this course need not worry too much about fab, because at least the dual degree micro will learn in their fourth year a full course on fabrication, VLSI technology. However, since we will never, others will never learn it, so I decided to show you at least how devices are made. Let's say I want to make a p-n junction. So obviously I must have one kind of semiconductor only possible. I can create one kind of silicon, either n-type or p-type, but I want the other one. So I must introduce the other impurities in the first one. So I may start with n substrate, add p impurities to make it p-n junction, or I may start with a p substrate and can introduce n impurities to make np junction. This is what. At the junction, what happens is most important. So let us say the how I make it. For those who actually the theory, or rather the thing behind technology, is much of chemical engineering, chemical physics, material science, name everything you know, optics. This is the only area where all engineering disciplines are required as much as you think. Even aero part, which is like Reynolds numbers, Gresham numbers, all kinds of theories are needed to actually explain the processes which go into fab. Why we want to know all processes properly? And because at the end I want to make a process on computer. Before I really commit my silicon to process line, I will actually make device in a computer, which is called using CAD tools. To create CAD tools, I need models. For every process I do, I need models, because then only numerically I can do something. That's called modeling. So modeling requires almost every kind of science you think will be required someday or the other in in our fab part. But let's see, assuming something we know, something we don't know. Let's say I have a semiconductor. To start with, n semiconductor, which has some resistivity rho, which is 111 oriented. This is given to you, okay. Rho is maybe 2 to 4 ohm centimeter kind of thing, maybe anything right now, okay. And if it is n-type, I would also say initially phosphorus doped or arsenic doped. All this data will be given. The wafers, I have shown you the first few slides, wafers are circular, this big ones. Nowadays this is 12-inch wafers are being, we started with working on 1-inch wafer. Now I can see 12-inch wafers. So this is only a cross-sectional part of the wafer. This is cross-sectional, seen from the across. So this is the thickness of the wafer, or rather one chip I am looking. Typically for 3-inch wafers, this thickness may be around 300 microns. For 12-inch wafer, it may be around 2 millimeters. Because that thickness has to be sufficient to hold that much mass. Silicon is extremely fragile. Okay. Of course, you must know that gallium arsenide is even more fragile. The joke is, if you see gallium arsenide, it may break. Okay. So silicon at least doesn't break by seeing, but if you put even little pressure somewhere, it chips. Okay, so this is starting wafer. Okay. Then the next process, I want to make an n semiconductor piece. So what is actually I am looking for? I am looking for something this. I have a n substrate, and certain region in this n area I want to make p semiconductor. So I don't want the rest areas impurities being introduced. Is that point clear? The wafer may be any size, the chip size may be even smaller. Each chip of a diode, I want selective area p diffusance. Is that correct? This will act like a diode. Then one contact here and one contact here will make a diode. So another word I use, contact. So I need something contact to p region and contact to N regions. Is that correct? This is the fab requirement. What is the first thing? I must be able to introduce impurity. I must be selective area, I must do that process. And then I must make contacts to both P and N. Okay. And in some cases, I want both contact on the surface, so I'll do another diffusion, we say later someday. Then this can act like a PN junction. So both contacts on the top. Okay. This is called planar device. Both contact, every contact is on the top. Right now this is vertical device. All integrated circuits do not have any back contacts used. We can use for some advantage, but not every time. Contacts are all on the surface. So we will do some more process. So complications, you want something more, you put something, and when I do this, I should not do this, or whatever impurity is going here should not go here, when impurities go here, they should not go here. So I must be able to mask certain area where things do not go. Mask means stop. Mask some areas, the rest where impurities can go. How do I do this? So the first process step I do, I actually take this wafer and oxidize it. Process is called oxidation. अभी जैसा सिंपल केमिस्ट्री बताता हूँ, सिलिकॉन प्लस 2O2 is SiO2. Actually, it will be something like this. This is essentially done why? Because 4 bonds have to satisfy, so you show like this. Now this looks a very trivial equation, but oxidation has taken our 50 years. We are still working on oxides. Okay. Silicon dioxide is a very tricky material, and it's one of the best material available to us for what? Mask. What does that mask? Silicon dioxide does not allow impurities to go through it. Is that correct? So SiO2 is an excellent mask. It is very good because whenever I heat this wafer in oxygen ambient, say around 800 degrees centigrade to 1150 degrees centigrade, depends on the temperature and time I keep, this I can actually, the way it will be, this region will get oxidized. Did you see something? I put half below and half above. What could be the cause? थोड़ा सोचो. वॉल्यूम ऊपर क्यों गया? आधा नीचे रहा, आधा ऊपर आया. Density of SiO2 and density of silicon are not same. Is that clear? So when I grow this, 0.5 micron roughly of silicon will make 1 micron of SiO2, okay, because of its density difference. So half of the silicon, 0.5 consumed in silicon, will grow 1 micron of oxide. So this is how, this for the sake of people who will not never learn technology, I thought I should show you. Otherwise we don't show every time half, we just grow on the top. Okay, so I have an SiO2 layer. So the first processing step is to convert silicon into silicon dioxide, which is now available for blocking impurities. Is that correct? This is sufficiently thick that any impurity entering here will not reach silicon. But what do I want? I want P impurities to enter. So from some regions I must remove my oxide, because only then I can introduce impurities in silicon. So the next process which allows me to do this, what I really look for is the following, though I will show you how I do. I am really looking for some kind of this structure. I must make an opening in SiO2 where then I can introduce P impurities. Please remember, when I introduce P impurities, this area will block, this area will block, only silicon which is now available to me, that area impurities can go, and then this area I can introduce impurities. Is that clear? So this is the called masking. The word used is masking. So how do? I use what we call Lithography. What is word lithography means? Litho means what? Some kind of a statue or earth part or something which is stable, okay, monuments, art, whatever you say, these are called litho. Okay. Graphy means replicate. Okay. So I do something on somewhere and transfer that on the silicon, and therefore it's called lithography. So what I do is, during this lithography, this is for those who may still find technology very interesting. I coat this wafer with another polymer. This is called resist. There are different kinds of lithography. One is called photolithography, in which light is shining. Ultraviolet light actually shines. If it is electron beam shining, that's called electron beam lithography. If X-ray beam shines, it's called X-ray beam lithography. If ion beam shines, it's called ion beam lithography. 99% we still do photolithography. We actually use ultraviolet to expose. Now this resist, therefore if it is for light, it is called photoresist. So if I coat photoresist, there are two kinds. One is called positive kind, another is called negative kind. Okay. This is called PPR, this is called NPR, negative photoresist, positive photoresist, PPR. Okay. Now there are two different. Positive negative means what is done in P will not be, same will not happen in N, or they must be complementary. Now this resist, let's say, is NPR. Okay, let's say this resist is NPR. NPR has a property that this polymer which you are resist is a polymer, carbon change. Okay. Now this regime is essentially right now open chain. That is, all carbon hydrogen chains are open. Okay. So what does that mean chemistry? If there is a open chain structure and I put this resins in some solvent, will it dissolve? Yeah, because all bonds are available to dissolve. Okay. Redox will be very fast on them. So all open chains carbon systems will dissolve fast. So what I do is, I take this and I create a mask. Now this is what we do. I create the mask which is on a glass plate. Okay. This is a glass plate, quartz plate, and whatever area I want resist to be removed, what should happen there? Light should not go there, because then only, okay. And this, another process of resist is that if I shine ultraviolet light on NPR, it will then become hardened. What is it word called? Hardened. What does that mean? The chain will get looped up. Okay. So if the carbon chains stuck together, then it is very difficult to etch in normal etchants. Okay. So it becomes hard. So now I want, can you tell me which kind, if I want to protect this much area, the rest part light should come. Is that correct? Then the resist will become hard and nothing can be done there. So I put a mask which is a glass plate coated with photoemulsions, in which this portion is dark. This portion is dark. The rest portion is clear, transparent. This is called clear field mask. Is that what clear? Clear field means most of the area is clear, only area which you want to etch is dark. Now this glass plate I keep in a process called lithography, which has this pattern. This is dark. I touch that wafer. This is a aligner system on which this mask is put on a wafer, which is coated with resist, and this is your mask. If I now shine ultraviolet light, typically of 2900 angstroms, okay, then which portion will not get light? The dark portion. Which portions will get light? Which is clear. So all this clear area will see the light. So this resist will become hard. Which portion will not remain soft? Wherever the light did not go. Is that correct? Then I take away the mask plate, which is here, and I have now areas of oxide which are protected by hard resist and areas of which are not protected by resist is soft photoresist. I developed this photoresist like a photography. I developed this resist. This cannot be etched because this is hard in a developer. But this resist actually goes. It's developed. Is that correct? So now do you see what do you see here? SiO2. Which areas SiO2 is exposed? This area. The rest of the silicon dioxide area is protected. Is that correct? Rest of the area is protected. This is cross-sectional, this is plan. Is that point clear? This is the plan. On the top you will see actually you put this. Cross-section you will only see this. ऐसा सोचो. इस प्लेन में देखो. थोड़ा ड्राइंग अभी करते हो कि नहीं पता नहीं करते तो सीखो. इंजीनियरिंग ड्राइंग का कोर्स अभी है क्या? है. चलो तो आपको एटलीस्ट यू नो क्रॉस सेक्शंस एंड प्लेन्स, plan and elevation, side elevation, everything. Okay. So I etch this. Now I dip this wafer into a etchant which only etches silicon dioxide. Okay. Silicon dioxide etched in SiO2 plus 4HF hydrofluoric acid gives you silicon fluoride plus H2. Match the numbers. It's called etching. Okay. So silicon oxide converts into silicon fluoride which is soluble and water. So if I put this into HF solution, then this area I see silicon dioxide has been etched. So what is exposed there? Silicon. That area is now exposed to silicon. Other areas silicon dioxide is right now protected by resist. Now I remove this resist. This is called stripper. So you must have another solution which even hardened resist can be etched. That is called stripper. Another organic material which will remove this resist. So this is the technology we learned then, because before that no one knew how to make device also. Okay, we made first time this. Okay, so when you etch this silicon, please, now, please, we have attention. So you have now, this area is protected by oxide, sufficiently thick, and some regions, yes, power. यहाँ पर ऑक्साइड था ना, उसको कैसे एच करें? विंडो सिलिकॉन खोलना है ना, so you remove HF. When you put in HF, only oxide etches, silicon doesn't etch. And since side was protected by resist, that does not etch on those sides. So only window in the oxide, silicon is now open. Which will be the area actually? This area is open in actually plan. This area, a window आपको ऐसा दिखेगा. Okay. So once I open a silicon and I remove the resist now, the clean things are available. By the way, the sizes of present day minimum size which we can do is nanometers, 28 nanometers, 22 nanometers. When I work, we are working on 5 microns. Okay. 77 to 2012, technology has advanced left and right. Okay. But anyway, that was the time then. Intel was also making 5 micron chips then. We were also making 5 microns. So there was no difference between Intel and us then. But now in India there is no fab. There is a fab in semiconductor complex Chandigarh, but it's not a great lab. They are now working on 0.18 micron, now going to start with them. So we are 180 nanometers is far away from 22 nanometers, but it's nothing wrong with it. Okay, so this area once opened, I now want to make what? Forget about this right now. I have now, as if I had done this, I want to introduce impurities. Which kind? The opposite of substrate, because otherwise junction cannot be formed. So if I start introducing impurity first inside this, by technique I will show you in a few minutes, which area impurities cannot go? This area. On a mass equivalently saying, this area will be protected, only the window will see silicon, so impurities can go there. Now there are two ways in which these impurities can be introduced. by us. Okay. One is called solid state diffusion. Why I am teaching in second year? Normally we have never, at least I have never taught this in second year course earlier, because there used to be fourth year course on what we call IC design and technology. That is defunct. I don't know whether it runs. And dual degree will always take care of that VLSI technology course. But since most of you will never see this, so I thought maybe today at least I should tell you how we make devices. So there are one method is called solid state diffusion, the other is called ion implantation. By the way, this is given in Streetman or Neiman or any book of devices. There is a part of the chapter initially is devoted to this. So you need not worry, you can go back and read again. Oh, this is called stripper. Most of the photoresist can be stripped in what we call as fuming nitric acid. Fuming nitric acid is 100% nitric acid. Because it has no water content, it fumes. Okay. That's what I say, this is the only area you need to learn thermodynamics, you need to learn chemistry, chemical, optics, everything what you need here, okay. Okay, so these impurities, please, these impurities either by solid state diffusion or by implants. First look at into solid state diffusion. What we do is, in a big furnace, quartz furnace, which is heated by roughly around 900 degree to 1000, maybe 1150 degrees centigrade, quartz tube, which is furnace, okay. And then from the one side, I put wafers inside on a quartz rack. Typically number of wafers in the actual Intel run will be 200 wafers per run, okay, 200 12-inch wafers will go in the furnace. So you can think what sizes of furnace they will have. So a lot of 200 wafers will get in, okay, put on a quartz big rack, like vertically. Once you put these wafers in, they also will get to this temperature. At that time we pass nitrogen, because even oxidation was done in the same way. We introduce oxygen or water steam, what we call pure water steam, and then it oxidizes. Now for diffusion, I introduce varieties of ways. One of the way I'll right now say, I'll introduce gas called phosphine, okay, or I have a liquid which is in a bubbler, which is solution called phosphorus oxychloride. This is for phosphorus too. If you have arsenic you want to introduce, we are doing P-type. For a P-type, we are normally either do boron gas, or actually the boron gas is B2S6, and here we use BBr3, boron tribromide, okay, liquid. So these fumes of boron tribromide are introduced in, or the diboron gas can be introduced inside, and along with this I introduce oxygen. These two will get oxidized and will release boron, You can see little chemistry, B2S6 plus whatever O2 you want to do, number correctly calculate, 2 boron plus some XH2O. Now this boron, and this is most important, you are getting some water also created there. This boron actually starts sitting here, and since there is the oxygen there, this become called boron oxide. What is boron oxide with silicon oxide? Can be called borosilicate glass. What is it famously known in the market? Pyrex, okay. Pyrex glass is essentially borosilicate glass. Borosilicate glass is a mixture of B2O3 plus SiO2. It's not a compound, it's the mixture of SiO2 and boron oxide in a lattice. It's called, matrix, okay. So this is called borosilicate glass. By similar argument, which will be the other glass? Phosphosilicate glass. or arseniosilicate glass. Okay. As2O3 plus P2O5 plus, all will be glasses. What is the property of a glass? They are essentially now contains boron. This silicon dioxide does not contain any impurity, but this silicon mixture here has created borosilicate glass at the surface. Is that? Further, since you are always H2O ahead, this will be always capped with silicon dioxide, because water will be larger, so some boron silicate will go down and the upper portion will be much more oxide. Now, this is called pre-deposition. I introduce impurity at the surface, but they are in the form of borosilicate glass. Is that clear? Now, if I introduce further, heat the wafer again in nitrogen, this is how the process of diffusion would come. This contains boron, and what does this contain? Very little holes, means practically no p-type. Okay, so what will happen? Large concentration of boron at the surface, no concentration, of very little concentration in the substrate. So what will do? It will do diffusion. So impurities start diffusing down. The time and temperature you choose, those many depths it can go, and will create area which is P times. Now question was asked last time also, how many impurities I need? Let's say I want the same concentration of P as of N. So how many impurities I should add per cc? Twice, because it should first compensate. Is that correct? However, this interesting, where is the junction? What is the concentration at this point? 0. So at the junction, we have 0 concentration, holes are, P and N are fully compensated. Is that correct? So that's the place where P and N are fully compensated. It's called junction. That word junction comes because of that. The net concentration there is 0. Is that correct? Net concentration at the junction is 0, because otherwise N cannot start. So at that point, P and N must balance, so that at this point, junction is created. Now how much deeper you want? This is called junction depth. And how many you want to have will decide by how much glass boron you initially create, how much, at what temperature you create, how much boron content it will have, how long you put this impurity which is diffusing down. The first process, as I say, was I called pre-deposition, in which oxygen was present. Next time no oxygen. The other is called, this word is very interesting, is called drive-in. Impurities are drive-in. So someone said many years ago, driving, he wrote in even exam paper, driving. I said, I'm not driving a car, but because I keep saying drive-in, so people thought I'm driving or something. So this is drive-in. By drive-in process, I'll be able, and during this oxide anyway is now closing the P area. So what will happen? Since the oxide is closed on the top and boron has gone in, what has happened? Now this impurity cannot come out, because otherwise they have all right for diffusing either side now. So the glass actually protects on the top, leaving the impurities. It goes down only in one direction and forms a junction. So I have now process in which I have created silicon dioxide even on the P area. Okay. Alternatively, I can introduce these impurities by what we call energetic ions. Yes, Paul. Just put the wafer in nitrogen oxygen ambient and oxygen ambient. Gas flow. एक वर्ड होता है मास फ्लो मीटर. I control how much amount of at given pressure oxygen or nitrogen go. किसी दिन तुमको यदि तुम्हारा कहाँ अपना चीफ किधर है? Okay. Maybe some afternoon which you are free, I hopefully, I'll ask my TAs to show you the lab. At least internally no one is allowed. Even I cannot go in, because unless I wear everything, I will not allowed. And not everyone has the permission to enter the labs. Okay, it's a very highly clean areas. because of that, but from the window we have big glass panel. You can see, maybe I will also present if time permits. Is that okay? But however, now PN junction is formed, but what is now we needed for the external world? I want contacts. Is that correct? I want contacts. Please remember, if I want, before that, so ion implantation, please, ion implantation is a process, I energize or put high energy ions. How do I energize ions? I have a charge, I want to give energy to it. What should I do? Pass through electric field. As it goes sucked up, it will get half mv square kinetic energy. Is that clear? So you act, and that is equal to the Q into E, force which you can create. Okay. So essentially I accelerate the ions which I create at the source, and those ions are sucked in and get energized. Then using a magnet, using Lorentz force, I can actually decide which angle the beam should come for the ion, and it should strike vertically orthogonal to wafer. That means if this is your wafer, ions must strike orthogonal. Okay. Once they strike, they have energy of 300 keV, very large energy, 2 minutes. Since they have huge energy, they hit the silicon lattice, and what do there? They will start losing energy because they are hitting. But silicon will also get displaced. Okay. So now ions can start entering in the silicon lattice. Is that clear? They will displace, get in, displace, get in, and as long as you do this, that much depth, these ions can get in. Then you drive in again, so more depth you can create, then you remove ions and just heat again as normal, and you will get junction deeper wherever you wish. Is that clear? So this ion implantation can be also for phosphorus, or for boron, or for arsenic, or for antimony, or any indium, any source I have which I can ionize, those ions I can actually pull by electric field. And how do I focus the beam? By XY deflector plates, both electromagnets. Okay, I can actually focus the beam. I may have a smaller beam hitting here, then hitting here. What is this word called? The way beams are normally scanned, what is it called? Raster. Are TV dekhte ho ki? The electron beam goes like this, flashback. It doesn't, because that is the flyback time. It's dark. So it comes back and again starts. But since the pixels are so close, you don't see there is a gap. Okay. That's why you actually scan any CRT. Okay. So this is raster. So actually the beam can be rastered. So if you have bigger wafer, you may start on the top row and keep. And as many times you will do this, as much impurities you can introduce inside. Is that clear? This is called ion implantation. This is the process we use nowadays. No one uses solid state diffusions. This is the process. Before we quit, last word, how will it look? If this is my concentration profile, actually this is minus, but let's say this is ND, which is the substrate concentration. From the diffusion side, I will introduce impurities in which we have a profile called Gaussian. Which profile? Gaussian. Okay. How would Gaussian I make? Like this. This will be looking like one side P, one side N. This is negative because opposite polarity. So this, in which one side is P and at the junction the other side becomes N, is called abrupt junction, P to N. In reality, there is no abrupt junction. There is a profile there. So we will actually solve all our analysis using abrupt junction. P on the left, N on the right. Is that correct? Ideal situation, which never occurs. And then we say, okay, if there is a Gaussian, if there is error function, if there is a linear, exponential, whichever real profile comes, maths, nothing great. You need little better maths. Okay. But you can always solve on system because computer does not mind doing n number of times without getting bored. So that's the help of computer. So we see you tomorrow. We'll finish this quickly now. How many mass do you think are still required to make a final diode? एक मास से P अंदर लाए. अभी एक मास्क हमको चाहिए जो इसमें विंडो खोले, P को कांटेक्ट करने, तो सेकेंड मास लगेगा. उसके बाद we will put metal everywhere, but I want restricted metal also up to only this. So how many masks are required? 3 masks. First to make window, second to make contact, third to make metal. So 3 masks are needed to create a simple diode. Okay. Is that clear? Typical ICs require 27 masks these days. 27 times you go lithography. Any error there is yield 0. Industry closed down. Okay. You should be accurate and super accurate. Okay. Then only you achieve something. Is that clear? So is point clear? So see you tomorrow again. I first thought not to do this, but I realized that you will never see this earlier anywhere else afterwards except dual degree micro. Thought I'll show you. See you then tomorrow.